Good morning. Good morning, Chris.
Morning.
How are you?
I'm doing pretty good today. How are you?
Good. Oh, it sure is windy out there.
Yeah, it is.
I went into a sneezing fit a little bit ago. How are the rest of you? See who we got here. We got Lord Melbury from the UK and Fudge from, I don't know, where are you from? Where are you from? Let us know where you're from. As usual, I'm a little behind today, so let me get all straightened out. Well, I prepared all weekend for a demonstration we're going to do today, so I hope it works out. I'm a little nervous that something's going to go wrong, but we're going to hope for the best. Oh, hi from Germany! Again, I apologize. I'm just getting things straightened out, ready to go. Tell me how things are going. Like, how are the projects going? You're all pretty much caught up?
I'm pretty much caught up. I started working on this week's lab. Started working on the last couple of days. So
The one where you're measuring the round trip time?
No, the one right before that, the
password cracking one?
password cracking.
Okay. How's that one going?
I've got that, I think, largely done. It's close. I'll probably finish it up tonight.
Well, now that I think I'm mostly caught up here, see if we can get started on this. All right, so as you can tell, I'm not like a young whippersnapper anymore. Let me turn this off. Been around for a little bit. So my computing experience began in the 1980s. I think I was in 4th grade when I was introduced to my first computer. My elementary school had bought a computer. It's called a Commodore PET, and it had, I think it had 4 kilobytes of RAM. And here, maybe I can find a picture of what that computer looked like. Oh yeah, this brings back memories. There we go. That's what it looked like. So it had a little tiny keyboard. You couldn't even like type like this on it. You just had to punch your fingers on it. The keyboard was only about maybe 8 inches wide, and had a little numeric keyboard here. And then this over here was a cassette tape interface. So if you've ever seen old school cassette recorders, the ones that are about this long and this wide, it had play button, forward, rewind, record, stop. That's basically what it had. And that's how you loaded and saved computer programs on it. So you turn it on, and then you'd get a little cursor up here in the corner that said ready, and then it was ready for you to type in your basic programs. You did all of your programming in BASIC at the time. I suppose there was some way to do assembly language as well, but for a 4th grader, BASIC was all we knew how to do. And so, like I said, this had about 4 kilobytes of RAM. Not much, certainly by today's standards, and even not much by the standards back then. And I'm sure this computer was probably really expensive at the time. But then fast forward to high school, which is the late 80s for me, and I began doing more programming, and by then I had an Apple II computer, and I actually have some in my closet over here. They're not the original ones that I had, but they're ones that are just like it. I'm not going to bring those out yet. I'm not going to bring them out today. But I started doing what, these days would have been talking to each other on discussion boards, kind of like, Reddit and things like that. And back then, we didn't have the internet. There was no, just plug your computer into the internet. There was no Wi-Fi. So if you wanted your computer to talk to another computer, you had to use something like a modem, like one of these boxes. Some of you may recognize boxes like this. It's basically a device that had a telephone jack on the back. You plug in your telephone cord into this, and that would go into the wall where your telephone service came from. And then it also had a connector in the back for connecting to your computer. This is called a serial port. And it's called a serial port because the bits are sent one after another instead of, as opposed to a parallel port in which the bits are sent along 8 wires simultaneously. So if you wanted to connect this to your computer, you then had to use a cable like this. And this cable would plug into the back of the modem, and then the other end would go into your computer. And then from there, you would fire up what was called a terminal application, and that would allow you to send commands to the modem, like tell it to dial a phone number. And then once the connection was established with the other end, you could then send and receive data. Usually the other end was running a program called a bulletin board system, a BBS. And there you could log in, you could post messages, you could download files, and mostly people used it for communicating with each other. And because phones back then, there was a distinction between local calls and long distance calls, you typically only called bulletin board systems that were in your city. Otherwise, it'd be too expensive to call ones that were outside your city. The long distance calls at the time would have been on the order of like 10 cents a minute. So even being online for 10 minutes meant that you had to, you got a bill for $1 from your phone company just for that. That was for like, just one session. So you typically didn't use long distance calling. And Chris is smiling because he remembers all those days of, nowadays you have your cell phones, right? You can call all around the world and it doesn't cost anything extra, right?
Yeah. I remember when that modem was high tech.
Oh, and this is actually a late model. Yeah. This one here. The very first one I had was 300 bits per second. Not like 300 megabits per second or anything like that. 300 bits per second, which roughly translates to about 30 characters per second. And if you are, that's to give kind of like an example what that's like, it's roughly the speed at which you can read on a page. Most people can read at about 30 characters per second, give or take a little bit. And then my next modem was 2400 bits per second, so 8 times faster. Oh my goodness, it's like getting a computer is 8 times faster. So now suddenly this thing is going 8 times reading speed, and now you can start scanning the text, right? You can just look at a message and go, I don't want to read that one, so you go to the next one. And then my next modem after that, remember these modems here probably cost in the order of $500 a piece, $300 to $500 a piece. So that first one was expensive, the second one was expensive, the third one I got was, and then I jumped all the way up to 14,000 bits per second. And that was in college when I finally got that. I actually went to college, went to university with that trusty 2400-bit modem, and then didn't upgrade to the 14 kilobit modem until I was like well into probably my second or third year at college. So when I was at the university, of course, we had programming assignments, and by then I had upgraded to a Macintosh computer. And actually, here's one that looks, let's see if I can get this. Here's one that looks very similar to what I had. Let's see if I can get this camera down here. So it had a whopping 9-inch display over here. And although on the camera here it appears to be blue, it is actually a nice crisp white display. It was actually very groundbreaking at the time to have a white display. There you've got a keyboard, a little mouse over there. So that's what my computer looked like when I went to university. And so when I wanted to do my programming assignments, of course, I could fire up like a Pascal compiler or a C compiler on that computer, but I wanted to run it, wanted to develop my programs and run them on the university systems, which back then were just command line Unix interfaces, not too much different from what you're using in our course today. Just you don't have the nice, pretty user interface. It's just simply the command line is all you had. And so I would be sitting in my dorm room or my apartment. I would tell the computer to dial into the university systems, and I would make a connection, and then from there I would do my programming. And I'd use a text editor like VI or Vim. Nano didn't exist back then. There was also Emacs. You could use that as well. But initially I did all of that at 2400 bits per second. It was serviceable. If you're just doing text, it's okay. It's not great, but it's okay. And it was certainly what we could afford to do at the time. But still, in the late 1980s, the internet wasn't something that you could just go and get a cable for and plug your computer into. Your computers didn't even come with any way to connect to the internet. They didn't come with Ethernet jacks on the back. They didn't come with Wi-Fi. All you had on the back of your computer was a place to plug in your keyboard, a place to plug in a modem, a place to plug in a printer. Remember, they're all cabled in. Maybe a place to attach an external hard disk or a floppy drive to it, and that's basically it. That's, in fact, on the back of that computer, that's all it's got, is those jacks on the back. So you couldn't do anything like just go and get an Ethernet cable from the store and just plug it into the internet, because that just wasn't a thing. In fact, in the late 80s, the internet was still something that was only found at really large corporations and at universities. So I was lucky to go to a university that had the kind of the rudimentary basics of what we would now recognize as the internet, although web servers didn't exist. And I mean, like, I'm sure for many of you, this seems like totally foreign territory, right? Yeah, how can you not have websites? How can you not have, videos to watch? How can you not have music to listen to? That all this stuff on the internet was basically just textual, like, you log into a computer and you could just work on your programs, kind of like what we do in our class right now. So what I wanted to do was kind of give you a little taste of what it was like back then to do what I was just describing, like use your computer to connect to a command line Unix machine and then, do some work on there. So this is what I've been working on all this weekend, is trying to replicate this experience as best we can, given that we don't have these giant Unix servers anymore. I don't have any way of dialing into anything using a modem, because those things just, there's nothing on the other end anymore. You can dial a phone number and all you hear is like someone's voice, right? There's no services you can dial into anymore. So this is kind of a useless piece of equipment now. So what I did was, in place of the Unix server that we would have had, I've got a little Raspberry Pi computer. This is a little tiny, let me see if I can bring this over here without causing anything to fall off the tables, because I have cables running everywhere. Here we go. I don't know if I can bring this in view of the camera, because it's currently tethered to a power cord, which is tangled up with everything else. Yeah. No, here. Let me see if I can find another one. There. I have another one. Here we go. Here's one. So it's a little tiny computer. It's got a CPU right there, Ethernet, USB. You know, when currently there's supply chain issues right now, so that you can't get these cheaply anymore, but they run about $40 or so. The amazing thing about this little $40 computer is that it can do everything that those servers could do back in the 80s and more, faster, with more memory, and way cheaper, and uses much less power. I mean, so basically, I've got a computer here for $40 that could outpace the fastest supercomputer back in the 80s. Just amazing what technology has done as far as miniaturizing things and making them more affordable. So I have one of these over there, like right next to me, but I can't bring it to you because the cord is too short. And into the USB port here, I plugged in a serial adapter. It's just a little gizmo that allows me to plug in a modem or plug in a serial cable. So what I've got, let me see if I can show you everything I've got here. I got the Raspberry Pi. And then, again, everything's tangled up here. On the end of that USB cable is a serial port. This one's a 9-pin serial port instead of the 25-pin I showed you earlier. And then over here, I have this other 9-pin, and that's going into the back of the Mac. So all I got to do is just connect these two together, like that. And now the Mac can talk to the Raspberry Pi as though it was connecting to a big giant Unix server somewhere. You following me? So let me see if I can get that to work. Okay, so imagine I'd be sitting in my dorm room or my apartment, and I'd go to my Mac. Sorry, I'm out of the camera here. I'd go to the Mac, use the mouse, launch this terminal application, and then press enter a few times, and you can see it says login. And then I would type in my username and my password, which I'm trying to do one-handed. There we go. And then from there, you can just do your work. It's just a regular old command line interface. Now this one is running at 9,600 bits per second. So that's even faster than my original experience of running it at 2,400. So it's about 8 times faster than that. So imagine this running at, not 8 times faster, 4 times faster. So imagine this running at 1/4 that speed. But still, it was usable. I could edit a program, I could compile it and run it. In fact, let's go ahead and do that. So, there's my little Hello World program. This one is going to print out Hello World, and then it's going to sleep for 3 seconds. And then down here I've got my shell prompt again, so I can type in clang. Oops, I'm trying to type one-handed with all this stuff in the way. Okay, I've got it compiled. And then there it is. Prints out hello world, pauses for 3 seconds, and then I get my prompt back. So that was my as far as developing C programs and Pascal programs, that was my experience back in the 1980s. I would be in my apartment or my dorm room, fire up my Mac computer, launch a terminal program, and then from there I would tell the modem to dial in to, actually dial the phone number for the Unix servers. Once I made a connection, I would get a login prompt, type in my name, password, and then I'm set. That's how everyone else did it too. And you have to also picture that back then in the late 80s it was very rare for somebody to have their own computer. Computers were really expensive. That computer that's sitting over there when it came out was about $4,000, which in today's money is about $8,000. So you can imagine spending $8,000 on a computer. That's a lot of money. So what's going on behind the scenes? What's going on when I actually press a key and that signal gets sent over the serial line to the other end? That's what I want to show you today. Not only am I trying to kind of recreate the experience of using a modem and a command line back in the 80s, but I also want to dig under the hood a little bit and show you what's going on when you actually press a key. So to do that, I'm going to need the help of this little box. All this box does is it sits in between here and here, and it lets me get access to the individual wires that are running through this cable. So I'm going to, watch this, I'm going to disconnect this, pop this in place, put this here. You can see these lights light up. And it's kind of hard to see because the lights are so bright. There we go. So all these green lights here are basically the signals being sent from the computer, and these two red lights represent the data being sent and received. And if I was to hit some keys on the keyboard, you would see these lights flash green to show the bits being sent across the wire. So basically all these other green lights don't matter. The two that matter are those two red lights right there. But the problem is the bits are going by so fast we can't see them. All we can see is a little flash of green light as the bits are being sent. So I'm going to do one better than that. What I'm going to do is I'm going to attach a device to these wires, and we can actually visually see the bits being sent. So give me a moment to do that. Okay, everything's gotten all tangled up. So I need to untangle things and then get this set up. This is the mess of wires I have to deal with. So we're going to need 3 wires. We're going to need a ground wire, and then a send wire and a receive wire. So the ground wire goes in. And then the send and receive wires go in. Excellent. Okay, let me move my camera into place. me set up something else here. So this device is called an oscilloscope. And what it does is it measures voltage on the vertical axis over time on the horizontal axis. And if I press a key on the keyboard on the Mac over there, we're going to see very quickly the bits flash by as they travel down the wire through that little box that had the lights on it, and the oscilloscope is going to measure the voltages as they go across. You see that? So I'm pressing keys on the keyboard, and once in a while the oscilloscope is able to catch those bits being sent across. So you can see the lines going up and down. But the problem is that they flash by so quickly, we can't see them. So I'm going to put the oscilloscope into what's called single mode, which is going to be able to capture one of those characters being sent across. So let me just press a key here, like boom. So I just pressed the letter B on the keyboard, and this is the waveform for the letter B. Now, the nice thing about these modern oscilloscopes is they have a little web server built into them. And so I can come over to my laptop and we can see that same waveform over here. So let me grab a screenshot of that. Actually, I'll put it back on this. Let me grab a screenshot of that and we'll put it where we can see it. Okay, so here's that same waveform that we just saw on the oscilloscope, but now I can do a little writing on it. So what we got here is we've got the signaling, and so down here basically is, down here at the bottom, it's kind of like 0 volts, and up here is about 5 volts or so. And the way these signalings work is every time you see it down at 0 volts, that actually represents a 1. And every time it's up at the 5 volts, that represents a 0. So we've got a total of, now, and also one of these divisions here basically represents 1 bit. So we have 1 bit, 2 bits, 3, 4, 5, 6, 7, 8, 9, and there's actually a 10th one right here. So there's a total of 10 bits being sent for that one character. So let's go ahead and label them. So this first bit here is called the start bit. Its purpose of going from 0 to 5 volts is to just let the other computer know, the computer on the other end know that a character is about to come. So it takes the voltage from 0 to 5, and that's kind of like just like turning on a light. It says like, hey, I'm about to send you a character. And then remember, on this signaling here, 0 volts is a 1, and 5 volts is a 0. So this is a 0. You see that? And then we got a 1, 0, whoops, yeah, 0, 0, 1, 1, 0, and then there's a last bit on the end called the stop bit, and that's when the signal returns back to 0 and lets the other computer know the character is now done. Let me see if I can make this a little brighter. 0, 1, 0, 0, 0, 1, 1, 0. Okay? So when the bits are sent from one end to the other, they're sent from least significant bit to most significant bit. So the first 0 is the least significant bit, and the last 0 is the most significant bit. So really, these are the digits 0, 1, 1, 0, 0, 0, 1, 0. And in hexadecimal, this is a 6, and this is a 2. And if we look up what that value is, see, here's hexadecimal, and we're looking for 62, which is right there, and we can see that is the letter B. All right, all that to send the letter B. And the cool thing about this oscilloscope also is that it can decode the bits also. So it understands what these bits mean, and right down here at the bottom it is written 0x62, which is the number we came up with right here, to let us know that this is decoded as the letter B. Right? Do you want to see that again? So let me put this into single mode, and then why don't you tell me what key on the keyboard should I press? Give me a key to press. A, Shift B. All right, we'll do A, but I'll do capital A, Shift A. Okay, there it is. So let me get a screenshot of that. All right, let's see if we can decode this. So here's our start bit. And then over here, let's count them. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's our stop bit. And so what are the ones and zeros that you see? See if you can decode this. What are the ones and zeros that you can see? Remember, a low is a 1 and a high is a 0. So up here are zeros and down here are ones. So if you just started watching the stream, what we're looking at is the actual bits being sent down a wire from one computer to another computer. So what I did was I pressed the letter A, Shift A, and then what we're looking at are the bits being sent down from my computer to another computer that are sitting on my desk. So what bits do you see there? Remember, a high signal is 0 and a low signal is a 1. All right, so we see a 1 here, then 0, 0, 0, 0, 0, 1, 0. So there's our 8 bits. And then we got to flip them around because the least significant bit comes first and the most significant bit comes last. So in order to put it in the order which we're used to, which has the most significant bit on the left-hand side, we just got to flip them around. So we get 0, 1, and then 5 zeros, and then a 1. And so this here is 4, and this is 1. And then if we look up what the value of 4, 1 in hex is, it's right there. Capital A. So just to clarify, the start bit and the stop bits are there just to let the other end know that a character is starting and stopping. Because the problem is that we've only got 2 signals. We've got a low signal and a high signal. And we have to indicate when a character is about to start. So you kind of want to get the other end's attention first, let you know, okay, characters are going to be coming. So we raise the voltage from 0 up to 5, and that kind of wakes up the other end and lets them know, okay, a character is coming. And then subsequent to that, the 8 bits roll in, and then there is a 1 additional stop bit when the voltage is brought back down to 0, and that goes back into an idle state. So down here, coming in, this is down at an idle, and coming out is also at idle, which lets you know that the characters nothing is being sent. So we go initially up to full voltage to let it know a character is coming. And then it just counts 1, 2, 3, 4, 5, 6, 7, 8. You get your 8 bits. And then finally, the voltage is returned back to 0 to let it know that the character is done. So every character you type on the keyboard has these 10 bits sent to it. A start bit, 8 bits of data, and then a stop bit for a total of 10.
Are they always in groups of 10?
I would say yes.
And if there was a second character following this, would another start bit just immediately follow the stop bit?
Yep. Yep. So you always have 2 bits of overhead for every character sent. This is what's called unsynchronized sending, in which you have to indicate, okay, a character is coming, but with that start bit, then you send your 8 bits, and then the character is done. And every character has that. So the other end basically gets woken up every time a character is coming in. There's also a mode called synchronous, in which the 2 ends, the reason why it's unsynchronized is because the other end doesn't know when the bits are going to come. You could press a key anytime. And so you basically have to wake up the other end to say, okay, now a character's coming. But there's another mode you can use, which is not used very frequently, called synchronous mode. And that's when the 2 ends are working in lockstep with each other. So they know when, so the sender is sending bits when the receiver is expecting to receive them. And in that case, when you have synchronous mode, you don't need the start and stop bits because both ends know when the bits are coming. But in unsynchronized mode, the receiving end doesn't know when the bits are going to come. And so you need to have these start and stop bits to indicate the beginning and the end of each character. Dean says basically that's called framing, right? Right. You got a start of this character and you got an end. So within that frame are the actual data bits that you're sending. In this case, the frames are really easy. It's just 1 start bit and 1 stop bit. Okay, so we've already seen that every character has a start bit and a stop bit, and then 8 intervening bits sent in reverse order. And we also know that this digital oscilloscope is able to decode these characters and do that work for us. But I wanted to show you how the bits are actually sent. But we know that it actually can decode the characters. So that's kind of nice. So basically any key that I press, it can just show us on the waveform what that key was in hexadecimal. We'd have to look on a table to see what the actual character was, but at least we can see the numbers. So that was my computing experience as far as dialing in were using a remote computer up until the early 90s, when suddenly the internet is around, but still in a very limited way. We still couldn't just go to the store and get an Ethernet cable and plug into the network because there just wasn't internet cabling in the apartments and in the dorms. You could maybe go to one of the high-end computer labs where they might have internet cabling running through it, but it was really rare. So the way we got internet access when we weren't on campus, when we weren't actually in our classrooms, was we did dial-up internet. You remember that? Maybe some of your grandparents still use dial-up internet if they live in rural areas. But it was basically, you got your modem like this, but instead of dialing into a command line machine, you would dial into a special modem on the other end whose job it was to translate the characters being sent into internet packets. It basically took the same signals that were coming down the Ethernet cable and turned it into signals that a modem could understand. And so that was called, dial-up internet. So I'd say from 1992 until 1996 or so, give or take, maybe even almost 2000 actually for me, dial-up internet was the way to go. And initially, I did dial-up internet using my 2400 baud computer. It was really slow. Then I upgraded to my 14 kilobit modem, and that was better. By the end of my college career, I was up to 28 kilobits, so it was going about twice as fast as that. But still pretty slow by today's standard, very slow by today's standard. But you have to understand that the internet back then wasn't a place to watch videos. It wasn't a place to listen to music. It was a place to read the news or post text messages to other people, or send emails, or get access to your computing resources on campus. Right? It wasn't a entertainment conduit that it is today. It was a place to get work done. So what was it like to use dial-up internet? Well, I can show you a little bit of that too. So let me see. What do I need to do to get that to work? Okay. So all I got to do on that Mac over there is put it into a mode where now, instead of sending characters to a command line computer, it's sending data packets out to the internet. And so my Raspberry Pi computer is going to act as a conduit. It's going to act as a dial-up internet server, which you would have used back in the 90s. You would have dialed into, you would connect your computer to one of these servers, and it would basically take the packets that were coming in from the internet and turn them into signals to be sent down the wire, the telephone line to the modem, and then from there to your computer and back again. So let me see if I can get that going. Okay, I think I've got it set up now. So I'm using this piece of software called InterSLIP. SLIP stands for Serial Line Internet Protocol. So it basically takes internet packets and turns them into something that a serial cable can understand. And then from there, you can launch a program to open, in this case, I'm going to open up a command line interface. Here we go. And then I got my login. Type in my password, and Now it looks pretty much exactly the same, but now this is coming over the internet. This is using internet packets, not just direct characters being sent, although it looks very similar. Now I could at this point launch a web browser and I could start browsing the web, but I got a couple of things working against me. One is the internet these days is really complicated. Like a typical web page, just even like going to the Google page, involves sending over 1 megabyte of data back to your computer. 1 megabyte of data over a slow serial like this is going to take several minutes. So even rendering the Google page is going to take a couple of minutes. And the other problem is that most web pages these days run HTTPS, the encrypted connection between the server and the client. And although this computer can do that, the protocols it uses, the encryption methods it uses, haven't caught up to the latest technology. So right now they're using 4,000 bit keys or 8,000 bit keys, and this poor little computer just kind of like rolls over and it plays dead. And in some cases, it can't even talk to modern web servers because it just doesn't have the computational capabilities to do that. The software is just not there. And so I could bring up a web browser, but it's very limited what I can do. I certainly cannot watch videos. I certainly cannot listen to music. All I can do is go to a very limited set of websites that are really designed to work with these older browsers, and there's not very many of them out there. So I could bring up a web browser, but it's just not going to be a very interesting experience to watch. But what if we could see the data being sent from my command line program, which is called a telnet application, to the Raspberry Pi? Remember, before, it looked like this. Every character had basically 10 bits being sent. A start bit, the 8 bits of data, and then a stop bit. But now, I'm not talking potentially to one computer. I could be talking to any computer out there that has a command line interface that I can log into, that I have a username and password for. So I can't just send 10 bits of data because I don't know who's on the other end. I also have to send additional pieces of information about what is the destination address, what's the source address. I have to send like packet numbers so that I can put it into the right order. There's a whole bunch of overhead that has to be sent just to send a single character. So here's a little bit of terminology. You may have heard some of these terms before. There's IP, which stands for Internet Protocol. And IP's job is simply to move data from one computer to another. That's all it does. So let's say you've got a piece of data that you want to send to another computer. And in networking terminology, that's called a payload. And you want to send it so that the other end knows that it got received, and it got received in order. So if I'm typing on my keyboard, I want to make sure the other end gets those characters exactly in the order that I typed them. So in addition to using IP, I'm also going to use something called TCP, which stands for Transmission Control Protocol, but that doesn't tell you anything about what it does. TCP gives you in-order, reliable transmission from application to application. So IP just moves it from computer to computer, and TCP moves it from app to app. So I've got my application running on my Mac over there. On the other end, I've got my command line shell, and so these are the two applications that need to talk to each other. I need to send characters from my Mac, and it needs to be received on the other end in order and without error. That's what in order and reliable means. And then conversely, in opposition, there's one called UDP, which stands for User Datagram Protocol. It's not used that much these days, certainly not as much as TCP is, but it gives you unreliable, possibly out of order transmission from application to application. So this is used for sending really short, like control messages across the internet. It's used for doing really quick things like looking up an IP address from a host name, in which you have to only can basically send out one packet out and get one packet in response. TCP is used for streaming data. It's used for things like video transmission, audio transmission, emails, sending chat messages. Basically, almost anything you do on the internet where you need to send data to the other end and it needs to arrive intact and in order uses TCP. So back to my picture. If you've got something you want to send to the other end, you got a payload, you are going to use TCP. So you're going to basically take that payload and you're going to wrap it up into a TCP packet. So you've got your payload, and on the front you've got a TCP header, which contains things like what port number is this coming from? What port number is it going to? What sequence number is this? Remember, it goes in order, so it has to be numbered. Also contains a checksum to make sure that it got to the other end okay. And then you're going to take that TCP packet and you're going to wrap that up into an IP packet. And that contains the IP address, or the source address and the destination address of the computer that is being sent from and to. And then that all gets wrapped up inside of a frame. Okay, so the frame for an individual character is that start bit and stop bit, but a frame for a whole packet is a little more complex. Okay, are we good so far? Now, in this picture, it's a little misleading. We don't actually physically take a payload and then put it inside of a box. What we really do is we just take like the payload itself, and then you just tack on some extra information in the front, and then you tack on some extra information in the front of that, and then finally you tack on some information on front of that, and you usually put also some information on the back end. Start bits and stop bits, basically. All right, so let's try this out. I'm going to press a key on that Mac, and we're going to see the bits that are being sent to the other end. Okay, here we go. Oh, did you see him go by? Oh, are we looking at that? We're not looking at that. Sorry about that. Here we go. See, every time I press a key, you can see all those bits rolling by. The problem is, you're going too fast. So let me do a little changing here. See all those bits? Here, we can actually watch it over here. Okay, but they're going by too fast. So I'm going to use the single mode where it's going to capture one of those sequences of bits, and then we're going to look at them. Oops, I forgot to put it in single mode. All right, so I'm going to press, I'll do Shift B like someone suggested. All right, there it is. And let me see if I got the whole thing. No, I don't think I did. Let me try that again. There. That's the whole thing. From beginning to end. And then if I zoom in, we can see down here at the bottom, the oscilloscope has decoded all of those bits. And I can also scroll. You can see what I'm doing over here. I can scroll left, and you can see these decoded bits down here. So looking down here, we can see the bits. The bytes represent C0, 45, 10, 00, 29, 62, B7, 00, 00, 40, 06. And then we can scroll to the right, and we can keep looking at those bytes. Are there any questions so far? I know I've kind of thrown a lot at you, but what I'm going to do, if you have any questions, go ahead and put them in the chat or just speak out, is I'm going to write down all of those bytes, and then we'll actually take a look at them. So I'm going to start by scrolling all the way to the left, and then start writing them down. So C045 100029 B7. Oops, I missed one. 62 B7 0000 4006 42 I just lost my place. There we go. BA, DB, DC, what is that? A8, 08, 97, 0A, 00, 02, 0F, 00. And 1708 0000. Oh, one more set of zeros. 00, FC, 2E, 37, F9, 16, is that 5E? I think we're almost done. Five zero 1 822. You can see there's a lot of data being sent for just one keystroke. Okay, I think that's it. Let's see, look at your question here. Is a frame sort of like a URL? No. I mean, a frame basically marks the beginning of a transmission and the end of a transmission, and everything in between is the data being sent. So one thing your browser does when you want to make a connection to a web server is it does need to send a packet out that says, here's the name of the server I want to connect to, here's the name of the document I want to receive. So it is kind of like it has to send a URL out, but the URL itself is not the frame. The URL would be contained inside of a frame. Is this insecure if you can detect the signals passing through it? Could you listen in? Absolutely. That's why these days connections to web servers are usually encrypted, because someone could literally just tap into the wires going out of your home and listen in to all the data being sent. My oscilloscope is on the serial line, but is it transmitting Ethernet frames? Well, it is kind of like an Ethernet frame. I'm not using Ethernet cables, so the signaling is a little bit different, but it's similar, right? You're going to get the same data. The thing about an Ethernet frame is that there's more stuff up at the front and there's more stuff on the back, but what's inside the frame is the same. So an Ethernet frame has a little more stuff up at the front. It's got things like what is called a MAC address, which contains the Ethernet address of the device you're sending to, and it also contains some signaling to make sure that no one else is using the wires at the same time, because Ethernet is a medium in which multiple computers can use it simultaneously. And so up at the front there needs to be some signaling that says, hey, I'm about to use the wire for a little bit, everyone else hush up. And then it sends its signal out, and then when it's done there's a signal in the back that says, okay, I'm done now. You can all go back to talking amongst yourselves. So what SLIP is doing is it's taking the internet packet, which is the IP address, the TCP information, and the payload, and it's wrapping up inside of a serial frame, which again is not quite the same as an Ethernet frame, but very similar. Okay, let's see, I hope I got all the bytes on there. I wish there was some way to count them, but there isn't. I mean, I wish there was a way to count them on the screen on you know, what I'm looking at over here. I got a total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then the next one would be, it was 36 altogether, 37, 38, 39, 40, 41, 42, 43. I got a total of 44 bytes on there. And I hope that's all of them. Well, let's hope for the best on that. So here are the bytes that I got. And again, I hope I got all of them. So they're really not arranged in a grid, of course. They're just being sent from left to right. So this line here really is just over here. And this line just follows that one. But now we're going to take these bytes and we're going to superimpose them onto the framing information, the TCP header, the IP header, along with the SLIP frame and the payload. So let me grab one of those. So here's the information about what a packet looks like. Okay, so the first byte being sent is the framing byte. So this is the start of frame right here. And then here on the end is the end of frame. All the stuff in between is what I'm going to put over in this chart. So this C0 here indicates the start of the frame, and the C0 indicates the end of the frame, and then everything in between is the IP and TCP information. All right, so let's start putting in. Each one of these boxes represents a byte. So this is a byte, this is one, this is 2 bytes right here, and each line represents 4 bytes. So here is 4, 5, 1, 0, 0, 0, 2, 9. You can see I'm just reading them off here from left to right. 6, 2, B7, 0, 0, 0, 0, 4, 0, 0, 6, BA, DB, A8, 0, 8, 9, 7, 0A. Oops, I missed something. I see, I actually do see that I missed a byte right there. So let me scroll this and figure out what that was. Oh, yeah. I just missed it right there. Four zero zero six 42 BA. That looks better. Okay, so I've gotten as far as right here. Okay, so let's take a look at what we got. So the first 4 or 5 indicates what version of packet is this and what is its overall length. So they've compressed 2 pieces of information into this 1 byte. So the 4 here means this is an IPv4 packet as opposed to an IPv6 packet. If this was an IPv6 packet, we would see a 6 there. And then this 5 indicates that the IP header, which is this piece of the chart, is 20 bytes long. You take this number and you multiply it by 4. Right, and we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it'll be a total of 20 bytes in this header. There could actually be more information, but 20 is the minimum. This is not so important. Don't have to worry about that. Right here, total length of the entire packet is not 29 bytes. It is 29 in hexadecimal, which is 2 times 32 plus 9. Whoops, not 2 times 32. 2 times 16 plus 9 for a total of 41. So everything from here down to here should be a total of 41 bytes. Are we good so far?
Yeah. Is that including the start and end of frame?
No.
Okay. That's
No.
within those boundaries.
Yeah, so it's basically this is going to be 41 bytes. Next is a packet ID number, and then what's called some flags and fragment offsets. So those are all zeros. Time to live is supposed to be basically the number of seconds that this packet is valid. And this is, of course, not the number 40. It's 4 times 16, which is 64. So this packet is valid for 64 seconds. So basically, you've got a total of 64 seconds before the other end will just throw away the packet. So it has to deal with it within 64 seconds or it'll be discarded. protocol is 6. 6 stands for TCP. So there's a chart you can look up what those numbers mean. So if this was a UDP packet, there'd be a different number there. If this would be like a ping packet, there would be a different number there. But this is a TCP packet, so we got a 6 sitting there. Next is the checksum. So this is, I think, a CRC checksum. It basically adds up all of the bytes in the packet, does some calculations on it, and then this is the number that comes up. But it's kind of like a hash. You can imagine it's kind of like a hash of the packet. Okay, so next is the source IP address, and that's going to be 4 bytes long. But I can tell you, having decoded these packets before, that this is the source address. It's a total of 5 bytes. Why is that? Well, I happen to know that the source address for this packet is 192.168.8.151. And so if we look at the packets here, this is 168, this is 8, and this is 151. Where's the 192? That doesn't look like 192. The hexadecimal value for 192 is C0. C0 A80897. But where's the C0? Well, the problem is that C0 is used to indicate the beginning of the frame and the end of the frame. So if you encounter a C0 in the middle of the frame, the receiving computer is going to go, oh, that's the end of the frame. We're done. So to get around that, the SLIP protocol says that if you're going to include a C0 in the middle of a frame, you have to send it as DBDC. So the DBDC there gets interpreted as a C0. Okay? This is a fundamental kind of problem in sending data to a receiver when the framing information could be a valid piece of data. Is you need some way to represent that data if it's not one of the framing bytes. And so this is how SLIP handles that, is if the data includes a C0, you send it as DBDC.
I was noticing that the length of the bytes within the frames was 1 more than the length, and that explains it.
This takes that into account, right? So these 2 bytes here became this 1 byte. That's why I was a little concerned at first when I went, I got 44 bytes out of this, and I know it's supposed to be 41, because I did this last night, right? So this DBDC became that. Okay, now we're on to the destination address, which is right here. 0A, 00, 02, 0F, and that is 10.0.2.15, which is the IP address of the Raspberry Pi computer. So this is the address of the Mac. And, oh, sorry, it's the other way around. Oh, yeah, that's right. This is the address of the Mac, and this is the address of the Raspberry Pi. Okay, and then source port is 0017, and destination port is 0800. See, am I interpreting that correctly here? And then sequence number is all this. 0000FC2E. Acknowledgement number 37F9165E. Data offset 50. Flags 18. Window size 2238. Checksum 23A8. urgent 0000 and payload 42. Okay, so source port here is, I believe that's 23. That's the telnet port number. And destination port doesn't really matter. Actually, what we're looking at here is not the character being sent from my Mac to the Raspberry Pi. We're looking at the response character. We're looking at the character coming back. So every time you hit a key, the fact that you see it on the screen means that it was sent to the other computer and the computer sent back a copy of it. So what we're looking at actually is the copy being sent back. Sequence number, it's just a serial number for the packet. And then this is the packet that's being acknowledged. So every time a packet gets sent, an acknowledgement is also sent back. And so this is the packet number that's being acknowledged. And then finally, here's the payload down here. Ignore all this stuff. This, it's not important right now. But there's the payload, 42. And that is the letter B. So all that just to send that one character. Oh, let me see if I can catch up on the questions here. So, is the DB-DC sequence also seen in the payload? Yes. So if the payload also contains a C0, then it'll have to be translated as a DB-DC. And then what's a port? So, so you know that every computer has an IP address? And a port is kind of like an application listening, or it corresponds to an application on that computer. So your computer will have an IP address, but if you're sending email to that computer, you will tell the packet that it needs to go to port number 25. And then listening on port number 25 is a program set to receive that email. Or if you're talking to a web server, you will send your packet towards port 80 or port 443. And then the web server will be listening to those ports and will respond to the packets coming in on those. So the port number basically distinguishes between applications running on a computer. And the IP address is just the address of the computer itself. It's kind of like if you've ever called a business, you dial their main phone number, and then you get like this, robot operator that says, like, if you want to talk to customer service, press 5. And if you want to talk to, the operator, press 0. And if you want to talk to technical support, press 6, right? You can think of those numbers you have to press as being like the port number, which identifies a specific service within that company. I guess that's the closest analogy that I can make. Good question, Dean. What if DB-DC is the desired data? Converting to C0 would be incorrect. That is correct. So there's an additional thing that says if you want to send a DB-DC, there's another way to send that as well. Let me show that to you. So yeah, people have thought about all this stuff. Okay, here it is. So you got C0, which is your frame start and end. And then it says that if you want to send the end byte, if you want to send a C0, you have to send these 2 bytes, which are this one and this one. So there's your DB and DC. And then if the escape byte, so if the DB occurs within your data, you're going to send this instead. You're going to send DB and then DD. So you're right. There are these little problems that if the data you want to send includes the framing information, you have to translate that framing information into something else. And then if that is some of the data you want to send, you have to translate that into something else. Is the destination address extra bytes coming back? You mean like the this one here? So every packet needs to have who it's from and who it's to. That way, the person, the application receiving the packet can send a response back to the recipient. All they do then is they just reverse those two fields. So you send a packet with the source and destination addresses in one order, and then the recipient sends it back with those things flipped, so that the person who sent the packet, or the application who sent the packet, knows that it came from the application that they were intending to talk to. Same thing with the port numbers. Those get flipped as well on the return packets.
How large can the payload be?
That's a dicey question.
It's more than a single character.
Oh, yes, it's more than a single character. In fact, that's what I was going to show you next, is what happens when a packet sends more. So an individual packet can be up to about 1,400 bytes long. But the payload can actually be up to 64 kilobytes. So if the payload is larger than a packet can hold, the payload is chopped up into little pieces. So your 64 kilobyte payload might be chopped up into 60 little tiny packets, each one assigned a different sequence number. And then the receiving end can then reassemble that into the original packet. And then what if your data is even bigger than that? Then those are chopped up into 64 kilobyte pieces, and then those are chopped up even finer. Does that make sense?
How does the receiving end know how many packets there are going to be in when it's received them all?
So these flags, where is it? Where are the flags? Right here. Contain information about, is this the first packet in a sequence? Is this the last packet in a sequence? And then these acknowledgement numbers and sequence numbers are used to order the packets within that. So if you see one of those flags, and they're just 1-bit flags, so you have a 1-bit that goes, this is a start packet, then the receiver will kind of memorize the sequence number of the start, and then subsequent packets are assumed to be in the middle, part of that transmission, and then the last packet will have that flag on the end that says, this is the end. And then it knows that was the last packet. And the sequence numbers just are serial numbers, so it's able to order them in the correct order. Okay, so let's go back to our oscilloscope here. And what I'm going to do is I'm going to run that Hello World program that you saw, that printed out Hello World and then paused for 3 seconds. And the pause is there so that we can see just the Hello World go by and not anything else. So let's put this into single mode. Oh, and I need to compress this down. And here we go. There. That's the packet being sent. And then we can zoom in. So this packet is longer. Oops, I'm sorry, you can't see what I'm looking at. There. So this packet is longer, but what I'm trying to do is just zoom in on the very end of it. Here we go. So here's that. Can you see that? Oh, you can't see that. Let me grab a screenshot of this. Okay, so here's the end right here. And then let's see, let's look at the ASCII values here. So 0A which I'm looking, I'm going to work backwards here. So 0A right there is line feed. This is carriage return. 2, 1. And all I'm doing is I'm just looking on this ASCII table here. So 2, 1 is exclamation mark. 6, 4 is D. Can you see what's kind of being revealed here? Can you guess what 6C is? L. 7, 2 is R. I can guess what 6F is. O. 7, 7 W. 2, 0 is a space. Six F is O, 6C is L, and then it goes off the screen from there. But that entire hello world sentence was sent in one packet. Remember a couple weeks ago I drew this diagram where you got a program and then you got standard output as kind of like this cloud, right? And your program sends data to standard output, and then that standard output gets buffered until enough characters are sent that it can just kind of spurt it all out as one packet. So although your program is sending behind the scenes one character at a time to standard output will hold on to it. And then when it finally sees that carriage return, that new line at the end, it goes, I now got a whole line. I can send it all at once. And if your program outputs, let's say, a whole paragraph of information, standard output will actually buffer all of that up and kind of wait for your program to go, oh, there's a little pause in your program. As soon as your program pauses for a little bit, it gathers all that information, crams it into one packet, and just sends it all out. That's the reason why I had to put that little pause in my program, because without that pause, you got hello world and then the prompt right after it, the Raspberry Pi prompt. And I didn't want that to be there. So I put that little pause in there to force the network to send out just the hello world, and then 3 seconds later, we would have seen another packet go out with the prompt information in it. Okay, but it's a long packet, and up in the front are the same 40 bytes or so. No, not exactly the same, but they contain source address, destination address, source port, checksums, sequence numbers, flags. So it's got the same 40-byte header, and then the payload is just a little bit longer. In fact, one of the things we could look at is, what does the length come out to be? So you remember up here, we had the length. So that was 1, 2, 3, 4 bytes in. Let's go and take a look at those bytes. So 1, 2, 3, 4. So the length here is 2A. Let's see, what is 2A? Is that 43? $42. Actually doesn't make sense, really. Why is that 2A? Right, because hello world should be like 12 characters long, 13 characters long. I'm trying to make sense of why that is only 2A. Actually, don't have a good answer for you. I expected that to be a bigger number. Well, that'd be something for me to figure out. Because that number, right, should be something like 50 something, not 40 something. All right. Well, again, I'll play around a little bit and figure out why that number is not what I expected it to be. I'm trying to make sure I'm looking at the right number. So we got 451000 2A. 62. Yeah, that's the right. Those are the right bytes.
Is that the right packet? There's not two packets strung together?
You know, I suppose that's possible. That's an interesting idea. Okay, can you see what we're looking at right here? So this is DBDC A80. So this is the IP address, and then here's the next IP address right here. So we're moving our way down the chart. Next is going to be the port numbers. So the 17 and then the 0800. Then next 4 bytes will be sequence numbers. I'm trying to move it so that it doesn't go entirely off the screen. So here's that port number, and then here's the sequence number, here's the acknowledgement number, data offset, flags, window size, right here, checksum, data. Oh look, 0D0A. So this is just the oh, I know what this is. This is the new line character when I pressed the enter key to run my program. You know, I typed in A.out and I pressed enter. That enter was sent back to me. So here's the, yeah, so that's what that is. And then here's the start of the next frame. So you're right, this is 2 packets all in one. It's 2 packets back to back. So now we start another packet, and that contains the hello world in it. That was a good catch, Chris. All right, so at this point, I hope you got a little bit of a glimpse into how data is sent on the internet. Now, you know, we use Wi-Fi these days, we use Ethernet. They both have their own way of framing the packets, but the stuff inside the packets is the same. They've got their own ways of sending the bits, but if you were to decode the bits, like we just did, you would see they would contain the same kinds of information. Just the framing information is different. Well, so are all packets like this? Basically. Even if you are viewing a Netflix stream, they're going to look like this. They're going to contain source information, destination information, checksums, sequence numbers, flags, ID numbers, time to live, protocol information. But in this case, the payload is going to be the pixel data for the video you're watching, or it's going to be the audio data for the music you're listening to. So we didn't quite get as far into my list of things to do today that I'd hoped. I'd hoped we'd also get to talking about the last programming assignment, but why don't we wait until Thursday for that? Nevertheless, if you want to look at that assignment, it is online, and you can take it. You can get the information you need, and you should actually be able to start doing it. There's one caveat, however, in the assignment. it mentions there are servers spread around the world. I currently only have the one for Fremont running. I need to spend a few minutes getting the one for like Sydney and London and Singapore and the other places up and running. And the goal is to be able to measure how long it takes data to get from wherever your virtual machine is. I think that's in, I don't remember where it is, but to send that all the way to another server and then come back again. You can measure the total time it takes to send the data out and to get a response back. And then we'll be able to compare that with each other to see whether closer ones are faster than further away ones, and also compare it to things like the speed of light to find out if the internet is faster or slower. Actually, obviously it can't be faster than the speed of light, but how much slower than the speed of light is it? Is it like half the speed, a quarter of the speed, a tenth the speed? I don't know, what is it? And I'm also, and we'll see if I have some time to do this, I'm also trying to cook up an alternative assignment for you, or maybe one that you could do if you get this one out of the way pretty quickly, and that is a Wordle server. So it's a computer you can connect to, and you can send and receive your guesses as to what the Wordle word is, and then it'll give you back clues. And if you've ever played Wordle on your phone, you know how this works, right? It tells you whether you got a letter in the right place, or a letter in the wrong place, or just the incorrect letter entirely. But it sends it back to you kind of like encoded, and then your job will be to write the front end program that actually plays Wordle for the user. So the user sees a nice textual interface, and behind the scenes it's sending this data back and forth about what the current guess is and what the response is. Then it needs to translate that into something the user can see. So I've got the back end of that working. Now what I have to do is write up some kind of assignment that allows you to write the front end. So that's also kind of in the works right now. So are there any last questions? What did you kind of get out of today? What was the most interesting thing you saw about today?
For me, it's just very interesting seeing the breakdown of how communications actually happen. How you can take a stream of bytes, and the sender and receiver both understand the structure of those bytes and how to encode and decode them and make sense.
It's really important that that structure be well understood by both the sender and receiver so that we could take those bytes and put them into the correct spots in this chart. So if both sender and receiver don't have this chart, then they can't make sense of those bytes. How about those of you who are watching on YouTube? What did you get out of it? I did this demonstration last semester, but I only used just sending and receiving one single byte. I didn't do this whole packet stuff. So that was what I was working on all this weekend. So Dean says you like the raw debugging examples of communications data. That's cool. Originally, I was going to do this demonstration with this old computer. This is a Radio Shack Tandy Model 102. This is a very early notebook computer. And this is also dates from the 1980s. If I turn it on. And you boot it up. Can you see that there? It's got a little menu. And it's only got a display. They can display 8 lines by 40 characters of information. But it runs on 4 AA batteries, and it runs for about 2 or 3 weeks on one set of batteries. And on the back, it's got a place to put in your modem, plus what do we got here? Printer. It actually has a built-in modem also, but the built-in modem can only go 300 bits per second, but you could connect up the phone line to it back over here. So here, so what I was going to do originally was I was going to go over to the telecom application and connect this up to that Raspberry Pi, and you could see what it looks like to use a command line with only 40 characters of information. But it's entirely usable, right? I can actually edit a program and compile it and run it, and it works. And again, I'm not running it on this computer. I'm running it on the Raspberry Pi. I'm just using this as a way to display that information. So that's originally what I was going to do, but then I hit on the idea of doing the whole internet thing. And that requires a more sophisticated computer. There's no way this computer can do internet. It's just the processor is just way not powerful enough. And the Mac over there can just barely do it. So the fact that we have computers these days that can watch videos and stream music and do everything that you do on your computer and do it almost in just a fraction of a second. It's just amazing. That I was bringing up a web page on that Mac over there, and it would be like 10 minutes to sit there and watch the bits flow in at admittedly 9,600 bits per second, which is not very fast. Realistically, you do it at 56 kilobits, which is dial-up speed, or maybe a bit faster than that, and then it's it's usable, but still pretty slow. Okay, so that's it for today. Hope you got something out of that. And I sure did. I learned a lot over the weekend, and it was a lot of fun setting that up. And now I have to go put it all back behind me. You can see if you notice behind me, there's a gap where that computer used to be. Lord Mirabari says, it was really interesting seeing the bytes get translated back into an IPv4 header. Good. I'm glad you got something out of it. All right. That's it for today.
Well, thank you. That was very helpful and very, very interesting.
Yeah, you're welcome.
All right.
Hey, have a good day.
You too.
Take
Bye.
care. Bye-bye. And those of you on YouTube, yep, thanks for watching. I hope you got something out of it. Looks like we've got 18 people watching, which is probably a record for me. So we'll be back on Wednesday. I've got my discrete structures course. I think we're going to talk about quantum computing that day. Just a brief hour and a half talking about quantum computing. And then on Thursday, we'll be back with the C programming course. And there we're going to finish up our discussion of computer networking and then start talking about other stuff as well. So I'll introduce the last programming assignment, maybe the last two programming assignments, and then we'll see where it goes from there. So Wednesday, quantum computing, and then Thursday, C programming, and then next week, I think I'll do a day on quantum computing, but in the C programming class. So it's kind of the same background information, but we'll explore how we could build a quantum computer simulator in C. That'll come up next week. Okay? Well, again, thanks for watching the stream, and I hope you all have a great day, and I'll see you next time. Bye-bye.